Okay. So we defined, you guys see my slides, yeah?
Yeah.
Yeah, okay. Yep. So we defined over here that when the sum of all the localities is greater than the total memory size. In other words, of all the localities of all the different programs. In other words, we said that you can have virtual memory, which means that the memory can be larger than the physical memory. So then the question became, how much larger can it be? And the answer is it has to be at least big enough to maintain the localities. In other words, the simple definition of locality, the most commonly used pages of every program. Whatever the current locality is of each program, it has to be big enough to maintain the sum of all of them. If we go beyond that, then our virtual memory is, the fact that our memory is larger than our physical memory is going to cause us a lot of trouble. It's going to cause us something called thrashing. Okay, the next slide kind of shows, it's hard to kind of understand this picture, but it shows like memory addresses, which memory addresses, like at time, 0, these are the memory addresses being used. At time 1, as time goes on, these are the memory addresses. You see that there are areas that are not used. Over here, this is not, this is used and this is used. The locality is here and here. And over here, the locality is Dafka is in the middle here, but not over here. So you see the locality over time changes. So what we'd like to have is a working set, which means we'd like to have, we want to somehow keep track of what is the memory that's needed by the process, by each process at a current moment. Now, this is for a given process. So like at time, in the early part of the program, maybe his locality is from 24 to 18, and also from 29 till 32 or something. I don't know, something like that. But at a certain point, it changes, and the locality becomes from 29 till 24, and also from 20 to 18. So we need to sort of change the locality. We need to keep track of what is the locality and make sure that the pages are of that locality are being stored, and that the total of all those pages is not too big. So we create something called a working set window, which is basically, if we're looking backwards in time, what, is if we at time X over here, we look backwards, we see that our window is, let's say, this large, so then our working set will include these areas. However big our window. If our window would be very large, then it would include all of these memory places, depending on how far back we look to determine our locality. So the working set is a fixed number of page references in the past that we will examine to determine how many frames of memory this process should be allocated. For example, we might look 1,000 references back. Theoretically, we should examine these old references at every clock cycle, since the backward-looking window is constantly moving forward. As we have this, I don't know if you see me. Do you see me?
We don't see you.
You don't see me at all. Okay. Well, that's a pity. Why don't you see me? Oh, maybe if I do like this. Why don't you see? Oh, because I have my video off. That's why. Here. Put my video on. And let's do share. Okay. And now you should see me. So, but I don't see me. Okay. Whatever. So, why is it like that? All right. So theoretically, we should examine these old references at every clock cycle. Every second, we have to look backwards, let's say 1,000 references. So as we move forward, we're looking back 1,000 from wherever we are. So we're constantly looking at a different set of 1,000 references. And then what would we do? Whenever a page fault occurs, if there are no free frames, we'd find a page not in the working set and evict it. In other words, as we're moving forward, we all of a sudden need a new page to insert. We don't have room. We'll check all of these references, and if one of them if there's a page in our page table which is not in this set of references that we most recently accessed, then he's an old reference. He's an old page. Get rid of him. Okay. And we said if the working set is too small, or not, if we make our, if we look back not far enough, we won't get enough pages. So if we only look back 2 references, then we won't have enough pages. And this is what I said before. If the demand, which is the total, the demand is the total working sets for all of the I's, for all the processes. If that's larger than M, than the memory that I have, then where you get thrashing. That's what I said. Well, this is a review kind of what we did last time. And here you see this idea of the working set model, where at a time T1, I look backwards a delta amount of references, and I see, in this case, I think delta is 10. So I look at these 10 references and I check, and I say my working set is 1, 2, 5, 6, 7, because those are the references from time T. But if I'm at time T2, then I look back at those same delta 10 references, page references. I'll only see that my working set is only 2 pages. That means I can have less memory. Now, how are we going to look back? Looking back sounds very nice, but how on a computer do you look backwards in time? So that's what the next slide I added explains. So let's take like this. If the delta is 10, like we saw on the previous slide, we need to maintain 10 history bits to know which pages were referenced in the past 10 references. The most significant bit on the left here represents the most recently referenced page. So for example, at T1, the most recently referenced page is 1. So on the page number 1, I have a 1 there. On all the other pages, I have a 0. But if I look backwards in time and I go back to 1 time period, which is the next digit, then I see there's a 1 at this 5. Why is there a 1 at this 5? To represent this 5 reference that happened at the previous moment in time. And then 7, if I go back to time another time, I'll see 7, 7, 7, 7, 4 sevens. That's the 4 sevens here. Then again a 5. Then a 1 up here. Then a 6, and we're just going back. So we have a reference of all of them. Now, what am I going to do? At each reference, every time there's a reference, every time I want to access a certain page, we will right shift the bits. In other words, we'll push them to the right. This 0 will fall into the abyss, and I'll have a space over here on the left, and that will be for my new reference at time 2, for example. So if you look at time 2, you see that this 1 has shifted over. This 1, everything has shifted over. There's a 0 here. Why is there a 0 here? Because the next reference was not a 1 again, but it was a 6. So I'm going to see a 1 over here on the 6. And then I push everything back. So now, if at any moment I want to know what my working set is, I can say at time T, my working set is anywhere that I have a 1. So 7 has a 1. It has many 1s, but it has 1, 1. That's all I need. So that's going to produce this 7 here. 6 has a 1, 2 1s, but it doesn't matter. As long as it's a single 1, I'm going to put them here. 5 has a 1, but now look at 4 and 3 and 2 have all zeros. That means they haven't been referenced backwards in time from the delta time period from T2, because we only go back 10. So I need a bit. Okay. Any frame, so it says like this, any frame with all zeros will be removed from the working set. So now I can keep track of exactly which references are in my working set. I have a method for doing it. There's a cost to this method. The cost to this method is, what is the cost of this method? That I have to constantly update these bits and shift them every single time I reference a page, which could be almost every operation. Not every operation is a page is a reference to a memory, but every load word is, every store word is. So you see that this will be expensive in the sense that it will take CPU resources. So this is not great, although this would be the theoretical working set method. So let's talk about a new thing, which is an approximation of the working set. How can we approximate? So a second, let me. To determine the actual working set, since the set changes constantly, we need to check backwards constantly. This is too costly. Instead, we will check back at defined intervals using a clock timer to tell us when to check. In other words, we're going to check only every, up to now we were saying we're going to check every reference. Now we're not going to check every reference, we're going to check every unit of time, which essentially means every unit of commands, instructions, more or less. So I'll look back 1,000 instructions and see all the page references. So how am I going to do this? So thus we will check for page references where delta is a time unit, not a reference unit, not how many references, but how much time, not a unit of page references. We now introduce a reference bit for each frame. So now each frame is going to have an extra bit on it. Actually, I have a picture kind of down here. You see a reference bit. In other words, for the page table, we'll have a bit, and that is the reference bit. Now, 1 indicates that it's been referenced. So let's go back to where we were. This bit is updated by the hardware. This is a hardware update, so it's very fast at every page reference. So in other words, we'll change it from 0 to 1 every time there's a page reference. So if we would wait, if our interval would be a long time, after a long time, eventually many, many pages will get a 1 next to them. Right? The more time I wait, if I wait only one tiny amount of time, then maybe only 1 page will be referenced that time. But otherwise, I'll probably get many, many pages that have a reference next to them. At every timer interrupt, which will not be at every, at a small interval, it'll be a large. Because I'll wait, let's say, a second, and then I'll see how many, and then I'll have a timer interrupt. And at that timer interrupt, I can check these R bits. Some of them will be 1 because they were referenced since they were referenced recently, and other ones will still be 0. At every timer interrupt, the working set bits, the same working set bits that we saw, are right shifted, and the R bit is copied to the most significant bit in the working set bits. Then the R bit is cleared for the next time. Thus, we keep track of which pages are referenced since the last timer interrupt. So look at this picture. Oh, wrong way. Look at this picture. We now have the exact same scenario, except I'm only having 5 bits instead of 10 bits. And at time t1, I will look back at the reference bits. Which ones will have a reference bit associated with them? Well, remember we said that basically when we're looking back here, we're only going to look at we're going to have a timer interrupt. Look at the sentence like this. We're having a timer interrupt from T1 to T3, which means every 2 units, every 2 time units. So that is, we're going to look back 2 time units. Let's call these time units now. So in the past 2 time units, what was referenced? 1 and 5. So you'll see a 1 and a 5 here. And if you look further back at what was the history? What does the history mean to us? We look at the 1 and the 5. Back further, it's 7 and 7. So if I go down here, I see 7. This single 1 indicates that twice 7 was referenced because there's no other 1 on this column. And again, a 1. Now, if we look further back, we're going to see 5 and 1 again. And that's what we're going to see. 5, and in the same column, 1. So because we have 5 bits, that means we're looking back 2 units of time. Every bit represents the amount, every bit has the potential, every bit represents what happened in a unit, in an interval between clock timer timeouts, between the interrupts.
Can I ask a question?
Yeah.
What's the difference between doing 5 bits here and before we had 10 bits?
Well, this is a simple example. Imagine instead of being 10, imagine that my interval was not 10, but 1,000,000. Then I'd have to have 1,000,000 bits. So, and now let's say that our interval, let's say we only want, instead of 1,000,000 bits, we're going to have 5 bits. And that means we're going to check every 1/5 of a million time. So in this case, it's not much of a difference. You only see 5. First of all, it's less bits to manipulate, first of all. Secondly, it's less often that I have to do the right shift and to check them. In other words, the hardware is going to be updating these ones. That counts as 0 time. I'm not going to count that as time. But the right shifting of this and the copying from the reference bit into these work set bits takes time. I'm going to do that now half as often. I'm not going to do it every time. I'm going to do it every other time. If I would change this ratio, obviously, and have only 2 bits, then I would do it much less. Or alternatively, if I had 5 bits, but my delta was instead of 10 was 1,000,000, and I had 5 bits, then I'm doing it only every 1/5 of a million time. Then I have to do the right shift. So I'm cutting down. In this example, I had to do it every single moment in time, or every single reference.
I guess I'm just confused on what the significance is. In T1/7, there are 2 1s. What's the significance of having those 1s in those specific places? Like, where does that come from?
No, well, first, the most thing is to look at this one. You understand this 1 and this 5? This represents, in other words, at this T1, when I look back, how far back am I looking? I'm looking back. I'm looking at the reference bits, these reference bits that got lit up. When did they get lit up? They got lit up since the last time I checked. Because every time, here, I'll read this line that I underlined here again. It's very important. At every timer interrupt, the working set bits are right shifted. So first of all, I move those bits that we just saw to the right. And then the R bit, the reference bit that the hardware put in, is copied to the most significant bit. Now, obviously, the more interrupts I have per minute, I'll have to do this more. If I have only 1 interrupt per minute, I'll do this very infrequently. And the more infrequently I'll do it, the more R bits there'll be, the more memory I'll have referenced. So then I'm copying them in, I right shifted to make space. Then I copied the R bit to the MSB in the set of working set bits. Then I clear out, I make 0 the R bit. So that until the next interrupt comes, the R bit will remain 0 unless somebody accessed that page. So I know now who was accessed between in the intervals between each interrupt. Is that clear, Zahava?
I'd have to go back and look through this again. I'm not fully getting it.
Yeah, it's complicated. If you have to look back, then everybody's going to look back. How many bits do we need now? So as I sort of said this, we need n working set bits per page table entry.
Can I just ask about the R bit? It turns 1 when you reference it, and then if you reference it again, it will turn to 0?
No, very good question. No, it will remain 1. In other words, if this is my situation, it means that at least once this page was referenced, at least once this page was referenced, at least once this page. This page was not referenced at all since the previous interrupt. And this page was referenced at least once. Could be referenced 10 times. However many times it's referenced, it'll be a 1. As long as it was referenced.
So we have no way of knowing if it was like.
We have no way of knowing if it was recently referenced or not recently referenced.
Okay.
But we do kind of have a way of knowing, because what we know is that it was referenced at least within the last interrupt.
Are you saying each interrupt, it resets to 0?
Exactly. At each interrupt, it goes back, everything goes back to 0.
Okay.
At each interrupt, it goes back to 0. So if I have my interrupts very frequently, then I'll have a greater knowledge of exactly when this happened. But I don't want them to be too frequently, because it's a lot of work to copy these bits and 0 them out and move them into the working set bits. So I'll have a large interval in general. And then that's why this picture makes sense, because a lot of times there'll be lots of 1s. Because lots of pages will be referenced since the past interval. Then I'll copy all these 1s into this column, the leftmost column. The next time it happens, I'm going to switch all these bits over. And the key point is that in this one, we only had 1 1 in every column. Here, because it's only the possibility is to have one. This is an exact representation of the history. This is an inexact representation of the history, because all I know is that since the last interval, in the previous interval, I had a reference to 1 and to 5. So I'm going to kind of know what my working set is. And then I said like this: how many bits do we need now? We need n bits, n working set bits per page table. That's the cross, a row. We need n bits, assuming we have n bits. This means that after delta divided by n time units, there will be an interrupt. So in other words, what I was saying is like in this example, our n is 5. In this example, our n is 5. So our time unit must be 2. See, our n here is 5. So our time unit must be 2. So that means you'll never see more than 2, ones here. Whatever, our time unit. It's really a little bit inexact here because these are references and we're talking about time. But okay. For example, if we maintain 5 bits of history, like in the next slide, and delta is 10 time units, as our delta is 10 time units, then we need to have interrupts every 10 divided by 5 time units. If we were to wait 5, let's imagine now we were to wait 5 time units, then every interrupt would represent 5 time units in the past. And we would possibly have 5 ones on a column. But that would mean our delta would all of a sudden gotten bigger, because if we have, then we'd only need 2 bits. Then we'd only need 2 bits, because this would represent the past 5 time units, and this would represent the past 5 time units. And then I wouldn't need all these other 3 bits. So it'd be actually, if I would do it like that and still have 5 units here and check back every 5, then I'd have a waste of 3 bits that are useless, because they'd be going back further than I determined my window to be. I determined my window to be only 10. I would easily have a window of 5, 10, 15, 20, 25. Okay. So that's this page, which is the working set algorithm with 5 bits, or really an approximation, like the title says here, of the working set. Yeah. Now the last 2, we already saw this slide a little bit, but we have one more slide here that I want to show you. As you can see in the previous slide, at time t5, look at time t5. This is t5. What's our working set? Everybody that I used in the past, well, even without this table, I can just see, I mean, visually, I can see that my working set is 1, 2, 3, 4, 6, 5, and 7. Because remember, it goes back 10. So it's 1, 2, 3, 4, 5, 6, 7. That's what's written here. And that's exactly what I have here. Here's 1, 2, 3, 4, 5, 6, and 7. Okay. What if the process was only given 5 frames by the operating system? In other words, fine, I just determined now that I've got to create a new I got to keep in memory all 7 pages, but I only have 5, let's say. What will I do? We will need to select a victim page to be swapped out. But who should I get rid of? Well, the truth is, the simplest thing to do, I mean, the most obvious thing to do is get rid of, keep this, and I know who to keep. I'll keep these ones. I'll keep these ones. I'll count up to 5 until I get a 5. And then I'll keep this one. But what if I have a tie? Or it's not necessarily going to tell me what to do. What if they're all referenced in the past, well, 2 can only, maximum 2, but what if a lot are referenced? So how will I select this victim? This selection will be based on age. The page who was referenced the least recently will be swapped out. But to do this accurately, we'll need to maintain a last reference timestamp for each page in the page table. In other words, we need to know exactly when he was last referenced. Because I don't want to just like sort of look, all I know is, in other words, if I just look at, wait a second. For example, here, if I look here, I know that 3 and 4 were referenced recently, but I don't know exactly who was older. So we'll need to maintain some kind of timestamp. Now, there's a problem with the timestamp because of swapping. We need to be able to disregard the effects of context switching on processes. So we will need to maintain an internal virtual time, because the context switching, remember, stops the process and then starts somebody else. So if we just stopped him, and the reason that his page references is old is because we have kept him stopped, because the operating system stopped him and let somebody else go, then it's not fair to consider him old. He's could be quite new. So we're gonna have virtual time, which is essentially how long he has been running. So we'll need to maintain an internal virtual time and a virtual time for each process stored in the process control block. Virtual time, as opposed to real time, considers only the time the process was granted CPU access, not when it was context switched out. At every timer interrupt, we'll update the process's virtual time in the process control block and the virtual time of the reference page table entry. So that's what I'm showing you here. This actually is a timestamp. And you notice that this is the oldest one, or actually this is the oldest one, 12, right? That's the smaller than 0 is the beginning of time. So this is a oldest one. The newest one is here, 2084. And here's our reference bit, and here's our timestamp. And this white block is like all the other information. In other words, like, all the things that we learned that is in a PCB. But these things are not needed for the algorithms, so we left it blank. But for example, what would be here is the page frame number. Sorry, not the PCB. Why did I say PCB? This is the page. Basically, this blank space is the page frame number, and the modified bit if we want to copy it back to the disk. Remember we have the dirty bit. So that's what the white part is. But this part, this is the actual page table information from what physical address, what physical address to go to. But I'm also going to keep this reference bit that it was referenced, and I'm also going to keep a timestamp. Now, what am I going to do with this timestamp? Now remember, I'm trying to select. Oh no, I'm trying to select a victim. At every timer interrupt, update the process virtual time in the PCB, the virtual time of reference paging table entries. Page P's age is the difference between the process virtual time and the time of the process last reference. In other words, I just take this number and let's say the current time is 2204 and well, that doesn't make sense. Wait a second. Oh yeah, 2204. And I want to know the age of this one. So I subtract 2204 minus 2084, and I get something like 120. So his age is 120, whereas his age is much older. His age is more like, more like 1,000. So that's the age. That's kind of obvious. At a page fault time, assuming all pages are referenced in the working set history bit. In other words, that's the worst, and that's kind of the worst case, that everybody is referenced, like I have over here. 1, 2, 3, 4, 5, 6, 7. Everybody is referenced. The table is scanned, and the entry with R equals 0, or if all entries are R equals 1, then the largest age is selected for eviction. So in other words, I'm going to, if I have to choose somebody, I'm going to choose somebody with the largest age. But also I'm going to check, see, this diagram, this is actually thinking about it without the WS bits. In other words, I could just do it like this. I could just say, if I don't have any, let's say I don't have any working set bits, then I'll just choose 0. Well, if I have 2 zeros, I'll choose the oldest one. But if they're all 1, then I'll just choose the oldest one. So I don't even need the WS bits. In other words, I want to get rid of somebody. I'll ignore the WS bits. I'll just look at whoever wasn't referenced right now. These ones were all referenced in the past interval. So these ones I'll keep, but this one wasn't. If they're all 1, then I'll just pick the oldest one. And finished. We don't have to do anything more. So note that we could rely on the age alone and not use the history bits at all. So why are we using the history bits? Because if we wouldn't use them, this would mean that processes would always use all the frames they were allotted. In other words, until I got to a state where I couldn't put anybody in a frame, I would just keep on, my window would keep getting big. I wouldn't have a window. I would keep putting people in, and then whenever I got stuck, I'd get rid of the oldest one. And then I lost the whole concept of a window. I would never shrink it. But I want to be able to shrink it when I see, like in this example, that the window is only 2 frames, 3 and 4. I would like to shrink it and free up that memory for other processes. So if I need to have the history, but I also need this aging. So we can combine these 2 things to determine and then use the history until I'm full. And then once I'm full, then say I'm full now. So who am I going to get rid of? I'll use the aging. This would result, if I wouldn't do the working set, then we'd be back to where we started. This would result in processes using more memory than necessary. Okay, that's that. This is a review of the algorithm. I'm not going to read it to you. The rest of this stuff we did. So that's the basic idea of the working set. The key points are to remember that the perfect working set would require as many bits as I am looking back in memory, as I need. Once I say no, I'll have intervals, then I can have fewer bits. And the working set is slightly less accurate. I mean, in this case, I don't know if it's less accurate. Is it less accurate? Well, not really. The total working set is still the same numbers that I would have had before. Times 3 here, it was 1, 2, 5, 6, 7, and it's still 1, 2, 5, 6, 7. It's not really less accurate. It's only, it's less detailed. Here, I could actually know who's the oldest based on who has a 1 the furthest away from the furthest to the right. Who's first one? Here, I don't necessarily know because I could have a tie. I mean, here I can't have a tie. Here I could have a tie. But that's because, and therefore we needed to enter in the aging. In other words, here I don't need aging because I know the exact times of when the references were. Here I don't know the exact time, so I need to enter in this timestamp here. Okay, that's that chapter. Let's look at chapter 10.
Also, when you say history, what's the difference between the history and the timestamp?
History, what I mean is like the history of the reference bits. Now, it's not an actual timestamp. It's just when. It's not a timestamp. It's just a bit to tell me that it was this long ago or that long ago. The timestamp is actual time.
Other than the reference bit?
What do you mean? What's the?
Not the reference bit? No, I just couldn't find where like the history part was in that particular example.
Here. That's sort of my term that I invented, which is I call these history bits. These bits are history bits because they tell me what happens if I read it from left to right, I'm going backwards in time.
So in the last one, we don't actually have like
this one, they're also history
just
bits.
The timestamps.
This one, they're history bits, but they're not 100% accurate because, for example, if I want to ask you at time 1, what was the previous reference? You might say, well, the previous reference, I don't know if it's either 1 or 5. How am I supposed to know? I have a 1 and a 5 here. So they're history bits, but they're not exact history bits. Of course, actually, for that question, I could find out the exact one if I had a reference bit also. And if I change it every second, then the reference bit would be 0 by the 5. and 1 over here. But still, 2 times ago, I wouldn't know, because for example, here, at time 3, it tells me 5 and 6. I have no way of knowing which one is older,
Right.
right?
there's
5 and 6.
going
But
to
if I
be-
look at this table, at same time 3, I can check 5 and 6, and I can see that 6 is, wait a second, 6 is already gone. Oh no, 6 is from there. Ah, because 6 has 2. You see, this one here is actually gone here. Oh, this one is at time 3, it's actually gone. See?
Mhm. You'll never have a reference bit if you have like a history.
No, you could have a reference bit. It's just not, you could know. Would, if you have a complete history, you're saying, if I do this,
Mhm.
nobody's ever going to do this. The point is, this is just theoretical. In this theoretical case, I wouldn't really need a reference bit, right? This
Right. No, I'm
theoretical,
saying, like, it would
no,
either have like a
yeah,
history or a
what?
time bit. It would either have
It-
a history or a time bit.
Essentially,
which,
these are reference bits, but
right.
they're not written by hardware. Wait, but I found an interesting thing here because of your question, which is that if I look at the correct history of 6, it says that he was used one time ago, and then backwards through the window, he wasn't used at all. Because this one, at time 2, it was used. But look over here at 6, there's a 1 here. Why is that? Because that's kind of the inaccuracy. That 1 carried over because, oh, wait a second, maybe it is it's a mistake. Oh, this is a mistake. Yeah, this is a mistake. Sorry, this is a mistake in this table. This 1 should not be there. See, it was this 1 here. It got pushed out. So it's gone here. All right, I'll try to fix that. Mistake. Wait, so you still have a question?
No, I got it. I was just wondering, like, if you'd have a timestamp and a history, and I was just like trying to figure out where the history was and the timestamp on whatever. Okay, thank you.
Right. It's a little bit confusing because here, this is in the page table timestamp. This is the actual page table. This is not the page table. I mean, it is kind of, it's an extension of the page table because this is the page 1, 2. This is an extension of the page table, but it's a lot more bits. And these are these working set bits. I mean, it's actually not all these bits. It's just 5 bits, but these are an extension of the page table. Really, we could have drawn this picture with those bits also here. And then I'd have 1 bit for the reference bit, which the hardware is updating. And then 5 more bits of working set, which is being updated by the software at those time intervals. Does that make it more clear?
Yes, thank you.
Okay, so let's go to okay, so we talked about the head moving here. The head goes forward and backwards. We call that seek time. Important to remember, that's seek time. As opposed to the disk turning, which is called rotation time. Here. So here I added some slides. This is also new. Where am I? No, not new slides. Okay. Seek time measures the time it takes for the head on the actuator arm to travel to the track of the disk where the data is to be recorded. So that's like what I said. It's this bar moving inward and out. This bar is not fixed. This bar moves in and out. So that seek time is the moving of the bar. And remember, we said that these are cylinders. We can view each track actually creating a cylinder with the other disks. We can sort of view it as a 3-dimensional cylinder. Seek times are not linear compared with the seek distance. You might think, well, the further I go, the longer it takes. Because of such a thing as acceleration and deceleration. It takes time to start moving. So, but it's not linear, but in general, we'll think of it as distance travel. The rotating drive's average seek time is the average of all possible seek times, which technically is the time to do all possible seeks divided by the number of all possible seeks. In other words, how many, in other words, from here, I could seek 1, 2, 3, 4. And then how long is each one? And then divide them all by how many seeks I did. That would be the correct way to do it. But in practice, it is determined by statistical methods. In other words, we're not going to actually measure it. We're just going to say, we can approximate average seek time by observing that average seek time is approximately half the maximum seek time. So in other words, if I'm at 0 and I want to go all the way to 100 or whatever the last cylinder is, if that takes 10 seconds, then the average is 5 seconds. Because if I'm at the beginning and sometimes I'm only going to go 1 second, sometimes I want to go 3 seconds. So the average will be half. Most common desktop drives typically being around 9 milliseconds. MS is milliseconds. Now, there's also such thing as rotation latency. Remember I said the seek time, which is to go forward and back. Rotation latency means I'm at this little track. I'm on this track, but I'm at this sector. Let's say I'm on sector. I want to get to sector S. I got to turn the disk. So it's also sometimes called latency. Is the delay waiting for the rotation of the disk to bring the required disk sector under the head. It depends on the rotation speed of the disk measured in revolutions per minute, RPM. And again, average latency is approximately half the maximum latency. And then there's something called a data transfer of a drive, also called the throughput. It covers both what? The internal rate, which is moving the data between the disk surface and the controller on the drive. In other words, reading it. You don't have a picture of a controller here, but like imagine at the bottom, after it read, there's a wire going through here to some kind of controller, which is then going to pass it on to the CPU. So and then there's the external rate, which is moving the data from the controller to the actual CPU. So all of that is called the transfer rate. The measurable data transfer rate will be slower of the two rates. In other words, since these are rates, they're going on simultaneously. I'm copying to the controller, and the controller is copying out. But meanwhile, while the controller is copying out, new stuff is going into the controller. It's like water going through a tube. The speed of the water will be the speed of the slowest place that the water travels. So as he came through here, maybe he slowed down over here, so there's going to be a little backup here, but that'll be the speed, whichever is the slower of the two. All right, now here's an example I took from the other slide, and I rewrote it because it was very confusing the way it was written. So this is, we got stuck here, and I rewrote it. So here. Now we want to, so again, we have latency, we have seek time, we have data transfer rate. What is average access time? Is the average seek time and the average latency. In other words, accessing to access the disk, to access the data. Not talking about the transfer rate, just to access the data, to get to it. So it'll be the combination. I got to turn, average seek time, I got to move the head forward, and then average latency, I got to turn the disk something.
Can I ask a question?
Yeah.
Does average latency refer to rotational latency?
Yes, that's what yes, every time, sometimes just called latency. In fact, I just call it. So the data transfer time is the average access time, which is these two things, plus, in other words, the data transfer time is for a particular amount of data. So it's the average time to get to the data plus the amount of data to transfer divided by the data transfer rate. That's this data transfer rate. So in other words, if I have 100 megabytes and my transfer rate is, well, megabyte a minute, then it'll take me 100 minutes plus the average access time plus whatever controller overhead there might be. And we didn't discuss that, but whatever controller overhead. If you're given that in a question, then you can't, you have to just be given that or not given. So, for example, given an average seek time of 5 milliseconds and an average latency of 4.16 milliseconds and a data transfer rate of 1 gigabit per second. Now, transfer rates are usually measured in gigabits because from the perspective of the disk, it's just reading bits. Bit. It doesn't know what a byte is, it's just trying to read. It's just raw data. So we usually measure it in gigabits. That's why you'll see a lot of times the B is small, and that means gigabits. If the B is big, then it's gigabytes. Because 1 gigabyte per second would be, actually, maybe, is there a possibility of 1? I don't think anything transfers at that speed. Anyway, it's 1 gigabit. Anyway, it'll be given in a question like it is. So the data transfer rate is 1 gigabit. And let's say the controller overhead is 0.1 millisecond. So to transfer a 4 kilobyte block on a 7,200 revolutions per minute disk, well, this is a misleading piece of information because I don't care about how many revolutions per minute because I was given the average access time. I was given an average seek time and an average latency. So I know the average access time. I don't care how fast the disk goes. And I'm also given this transfer rate. So this is extra information. Don't let it confuse you. So to transfer a 4 kilobyte block on this disk, how long will it take?
I think I'm confused.
Well, this information is not necessary. The point is, if I want to transfer a 4 kilobyte block, how long will it take? Well, it's going to take it's going to take 4 kilobytes divided by whatever the transfer rate is. So that's, what is the transfer rate? Well, what's 4 kilobytes, first of all? 4 kilobytes is 2 to the 12th, right? 2 to the 10th is a kilobyte. 2 to the 12th would be 4 kilobytes. Divided by 1 gigabyte. 1 gigabit. Now, if it would be a gigabyte, it would be 2 to the 30th. But it's not a gigabyte, it's a gigabit. So it's 2 to the 27th. We take 3, because 8, there's a byte is 8 bits. 8 is 2 to the 3rd. So I just simply remove 3 from the exponent, and I get 2 to the 27th. Now, if I do the math, I get 0.031 milliseconds. Now, but that's not the answer. Because it's that plus the average seek time, average latency, and the controller overhead. So I've got to add to that 5 milliseconds and 4 milliseconds, 0.16, but at 0.1, so 0.26. So it's going to be, I should have, where here? Let's write this out. Total, yeah, I don't know why I didn't write this. Total equals 9.16 plus 0.1 plus 0.031 equals 9.2, right? Because I add the ones and the ones go together. And then I'd like to write a 6, but I got a 3 over here. So it's 6 and 3 is 9. And then the 1 milliseconds. Yeah? That would be the time to transfer 4 kilobytes on this disk. Okay. Now this we talked about. These are the cylinders. These are talking about head moving the head back and forth. We talked about these different methods. First come, first serve. Shortest seek time, moving the head forward and back first. Then we talked about the scan, also called the elevator, where I just go up, 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 up. I move the head in one direction. Remember, we're talking about this head here. If I want to get like something on cylinder means essentially track, right? Track and cylinder are synonymous, except that a track is on a one-dimensional, it's on the platter, and that this is a different track, but it's the same cylinder. So but when I move the heads, I move them all together. So we can talk about cylinders. So if I want to go to cylinder 1, then cylinder 7, then cylinder 138, now I'll go up like an elevator, and I'll service everybody until I get there, and then I'll go back down again. So if this is my queue, if I have a queue of requests, I can look at the whole queue and I can say, oh, I'm going to go, I can just go to the queue as it came. That's first come, first serve. Or I can say, oh, I'm at 90, I'm at 53. I'm not going to go to 98 because I'm going to go to the closest one, which is 65. And I'll go up, 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 closest one. Now, that's shortest seek time first. What about scan? Scan says, well, it depends what I'm doing at the moment. If I'm at 53, I'm not going to necessarily go to the closest one because I might be, because closest one might mean I'll go, right, I'll go up, 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 up to 65, and then I'll go down, 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 down. The elevator would go up, 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 and then start going down. And meanwhile, somebody's waiting over here, and he thought, oh, he was very optimistic. He thought he was going to finally get to him, but he didn't. He turned around and went back down. So scan says, no, 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 we're going to be consistent in our movement. We're going to go, if we're at 53 and we're already going down, then we're going to keep going down. And we'll just service whoever's on the queue in a downward direction. So the next one will be, what is 37 from 53, and then 14, and then I get to 0. I get all the way to the bottom, hit the bottom floor, and I go up, and I start hitting whoever's in my queue. It's like I kind of, at any moment, I check who's in the queue and see if there's somebody there, and that's how I determine my order. And then we said, that's scan. So C-scan is similar, except it's more like a Shabbos elevator. I always go up. So if I'm at 53 and I want to go down, I can't. So I'm going to go up, 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 and service everybody who's going up. And then I'm going to run to the bottom and start going up again. The only reason I would do an algorithm like this is because the hardware is faster. It's faster to move that head forward and then bring it all the way back, and then forward and all the way back, than it is to sort of move it in two directions in a controlled way. It's just a hardware question, how it was built. And then there's the same kind of thing, except that instead of going all the way to the top floor and all the way to the bottom floor, I stop early. This we talked about before. That's it for chapter 10. And let's do chapter 11.
I thought it was 12.
12, whatever. I noticed actually that in some of the people who teach this course, like they called it chapter 11 and some called it 12. I think it depends on the book, but I'm calling it 12. You're right. I think this one I didn't change. Anyway, what I just did for you was a lot of information. So you can have to go over it again. If you have questions, you can SMS me or message me, I guess you say. But it was review because we actually did pretty much everything we just did now. We did it except for the first part. Even the first part we did a little bit. From current slide. Okay. Chapter 12. This is also shortened. Now we're talking about file system implementation, or how we allocate files to our hard drive. Before we were talking about memory, programs in memory. Now we're talking about our hard drive, files in hard drives. So we could have a directory like this. Count is a file name, and he starts at location 0 and goes for 2 bytes. So it's 0 and 1. TR is another program. He starts at location 14 and goes 3 bytes, 14, 15, 16. And I'll have some kind of directory and tell me where it starts and how big it is. Now, if we're talking about accessing it, we'll have, this is similar to what we've done before, we'll have some kind of logical address. And part of it will be Q and part of it will be R. The Q will be the starting address, and the R, there's this 0, this 14, or this 19. And the R will be how far into this file I want to go. So R will be, if I'm on file TR, then my Q will be 14, and my R will be how many bytes I want to go forward. Which byte I want to read of the file. Those will be a number like 1 or 7, some number relative to the beginning of the file. Okay. I'm skipping that. Okay, then there's two other methods of allocating. This obviously is problematic, this contiguous allocation. For the same reasons that we said that memory allocation that's contiguous is problematic. Which is that I can have a section, I can't necessarily use, if I have a file that needs a lot of space, and there is the space, but it's broken up like it is here, 17 and 18 are available, but I can't, if I want to combine it, if I need a file that's 1, 2, 3, 4, 5, 6, 7, 8, no problem. But what if I want a file that's 9? So I have a problem because this is 8, and I really have a 9th place, but I can't use it because I need contiguous. So we need to overcome that problem. What is that called, by the way? If I
The internal fragmentation.
Exactly, external fragmentation. We want to overcome this external fragmentation because we can't put we have like unusable space. We have space, but it's unusable. So the one method is to have a linked allocation, which is that each file is really just a linked list of all of its blocks. The file ends at a null pointer. Each block contains a pointer to the next block. That's the key point. There's a picture of it. I don't know why they don't. Yeah, here. Here's a linked allocation. We start at 9. And the end, we could keep track of where the end is, but we don't actually have to, because the 9 tells us where to start. And inside of this part of the file, there's also like a reserved area inside of the block of memory that's used to locate the next block. So I sort of lose a little bit of my data. I can't use the full block for my file because a small part of it is going to be a pointer. And that's going to point to the 17. And then that's going to point to 1. And that's going to point to 2. Meanwhile, I've gotten 4 blocks of my program. Finally, 2 points to a block, but the address at that block is not the address inside of that block doesn't point anywhere else. Its address is negative. In other words, -1 is actually a real block of the file. But in its address location, when it should be pointing to another place, instead of pointing to another place, it has a -1 there. And -1 is an invalid address. So then I know that I've reached the end of the file. That would be called a linked allocation. It's like a linked list where the last piece points to null. So you see here's a block. It has a pointer in it and its data. Now here's a key point. Well, first of all, let's read the points, all the points. No compaction is necessary. I don't need to do compaction. Remember, we talked about compaction when we were talking about memory, but you can do the same with contiguous. You'd have to do compaction to get rid of fragmentation. And there's no external fragmentation. Free space management system called when a new, right, you can easily increase the size of your file. Imagine if you had a file and all of a sudden it got bigger and you had contiguous. You'd have to find a whole new location to put the whole thing in. Now I can just find one more block. Now, this point is actually the most interesting, which is you can improve efficiency by something called clustering blocks into a group. In other words, instead of you can group your blocks. Remember, we're gonna, in our page table, there'll be block size. These will be block sizes. But here it's kind of a pity. If I'm talking about just to locate them, I don't need to have things so small. What I can do is I can say, I'll say, you know what? I'm going to take every 2 blocks and I'm going to call it a cluster. And then I'll have in the cluster, only the first element in the cluster will point to where the next cluster is. And then the second one, I don't have to waste the pointer and I don't have to jump. I don't have to like do a read from somewhere else. In other words, most files have a certain, decent size. So I'll make my cluster, be 2 or 4 or some number of blocks. And then I'll point from one to the other cluster. So I'll save in hopping around. I won't have to read from one location and then go read from another location all the time. I'll be able to stay in one location for a while longer. That's called clusters. There is a terrible problem with this. It says reliability can be a problem. And it also says locating a block can take many I/O and disk seeks, right? To find, I want the 5th block, I'm gonna have to go hopping around to get there. So the clusters will help us, but of course the clusters will increase fragmentation. But even if with clusters, I still have this problem of jumping around. Whereas I didn't have it in contiguous. I could just jump immediately to there because I just do the math. I know where it is. Reliability can also be a problem because if I lose a pointer anywhere along the way, then I lose the whole file. And I have no way of regaining it. I'll have if all of a sudden I lose this pointer, I don't know a picture of it here. Where is the picture? If I lose this pointer from 16 to 1, then I have no idea what the next one is. And I also have no way of ever freeing one. He'll be assigned. I won't know that which file he belongs to, and I won't be able to reassign him. Okay. Where were we? So that's the linked. So then there's another system called FAT, F-A-T, File Allocation Table. The beginning of the volume, or the volume here just means like the beginning of the disk. It has a table, a file allocation table, which is indexed by block number. In other words, the indexes in the table represent block number. So if I want to go to block number 20, I just simply go down 20 rows. Let's see how it works. So here, it'll say, here, the file name test. Sorry, wait a second. Right. Okay. So in the directory, I'll have a file called test and some other information, and also where its start block is. Now, if it's start block, all I need to know is the starting block. So it's kind of like a linked list, because here I also know where the start was, 9. Here I also know the start is 216. But instead of, and sorry, then what I have is, instead of 216 pointing to the next one, this fat table points to the next one. So in other words, 216 is somewhere over here on the left. It's some memory. This is not the memory. This is not the disk. This is memory, this fat table, or this is actually stored on the disk also, but it's in a certain location on the disk, which is fixed. And this fat table becomes like the key to everything, because my directory just says that test starts in block 217. So I go over to my fat table and I go to line 217. And first of all, if I just wanted the first block, I don't have to even use the fat table. I already know. Go to 217 and I'll go to the disk in block 217, and there's the beginning of my file. But if I need to know the next part of my file, how am I going to find out the next part? So for that, I'll go to row 217 in the fat table, and there will be written 618. What does 618 mean? 618 means that's the next block I need. Great. So now I can read the next block over here in the disk. I should add to this picture, like a picture of the disk. Now I've read 618. I need the next block. How am I going to know what it is? No problem. Since I was just reading block 618, I'm going to go to row 618 in the file table, and he's going to tell me 339. Oh, that means the next file I need to read. Now I'll go over to the disk and I'll read 339. If I need the next block, I'll go to 339. And if it's blank, then, or -1, doesn't really matter. Actually, it has to be -1. It can't be blank, right? I don't know why they drew it here as blank, but it should be really -1. Then I know that I'm finished, that I can't go any further. So what's the advantage of this? The advantage of this is that I have basically what I did was I took all those pointers that were spread out here in each block, and I focused them into one location. It also means it's going to be faster for me. I'm not going to have to seek so much. If I want to get, in other words, here, if I wanted to get to the last file, over the last part of the file, I'd have to move my disk head up and down till I finally got the last one. I have no idea where it is until I get there. Here, since it's all in the fat table, I can move my disk in a limited space. In this space is all right next to each other. This fat table is all near itself on the disk. So the head won't have to move so much. I'll save in latency and in seek time. Questions? Now, the third, let's say the third method, the final method that we'll talk about, I think the final method, is indexed allocation, which essentially means you take the fat table and you stick it in the first block. You take the fat table and you take a small piece of it. Now there was just these, you're not having a fat table. We're not going to use a fat table. So I shouldn't say you take the fat table, but the concept of a fat table is applied, but it's applied in a different way. How is it applied? Into the file itself, you're going to put the information about the file. But unlike in this one, where the information is spread out throughout all the blocks, I have to, if I want to get to the last one, I got to go through this whole wild goose chase, or what is it called? Treasure hunt, till I finally get to the last place, and then I can know where it is. Here, what we're going to do is we're going to say, you know what, let's sacrifice the first block of the file. His whole job will be to keep track of where all the other blocks are. So in the first block of the file, I'll put, where all the things are. The first one is 9, then 16, then 10, 1, then 10, then 25, and then a whole lot of -1s because I didn't use that space yet. But it's there and available for me in the whole block. I got a whole block for locating other blocks. So this is, in a sense, you can say, well, it wastes a block. That's true, kind of. It wastes a block. It's also limited in another way, which is that, what if I need 2 blocks? What if 1 block isn't enough for my file? It's a very big file. But yeah, what is the advantage over fat? One problem that people had with fat is that sometimes, like, that section of the disk got overwritten or got, corrupted, and then you lost your fat table. You lost every single file in your program. If your fat table got somehow corrupted, the whole thing, then I can no longer get anywhere any files. I have no access to them. I don't know what the order. They're all mixed up. I can't reconstitute my files. So here, wait a second, where were we? In this method, let's say I might lose 1 file, but I'm not going to lose everything if the disk got corrupted. Right, we don't need, we do need we need these index tables, obviously. It also allows us random access. If I want the 3rd block, I can just read down. It's even faster than a fat table. Fat table I have to jump around. Here it's just in order. I have dynamic access without external fragmentation, but we have an overhead of an index block. Right, in other words, I need this overhead. I have to waste this index block, but I do have direct access. Okay. Mapping from logical to physical in a file of maximum size 256K bytes and a block size. We need 1 block for index table. Correct. Okay. Now we're going to have the same issue as we did with before. We're going to maybe have to have multi-level index. Oh no, what does it say? Yeah, outer index and inner index. Why do I need that? Because I may need a larger file. If I need a larger file, then I might have to have multiple levels if my block size is not big enough. I need 2 blocks, let's say. Well, first block I used up. I need another block. If I need another block, all of a sudden I need to have a block to tell me where the 2 blocks are. So that problem I wouldn't have had in either the FAT system or the linked list system, because either way, I just keep adding stuff. Here, as it gets bigger, I'm going to have more levels. So what's performance? The best method depends on the file access type. Contiguous is great for sequential and random access. Linked is good for sequential, but it's not good for random. In other words, if I want to be able to jump to the middle of my files all the time, then the linked list is not good. Index is more complex. Just to get to a single block of actually my file could require 2 index block reads, because I've got to read the outer table and the inner table. And then finally the actual block read. So it's going to require 3 reads. Clustering can help improve throughput, right? I could also do clustering in either the linked list or the index method. All right. Yeah, this is a this is just this is not that important, but I'll just mention it. Free space management. Obviously, I got to keep track of where the free parts of which blocks are free. I can have some kind of vector where I map every single block, whether it's free or not free. Remember, here I just map where it's free or not free. I don't mention who it's assigned to. And that's why I was saying before that if I lost one of my links in the chain here, I no longer, all I have is listed that it's occupied, but I have no idea by whom. I could find out. I could find out by sort of by process elimination. I can go through every single file and see if it's in him. And then if I see it's not in any of my files, then I can remove it. But normally, in other words, when I delete a file, I'll go through my file allocation table and I'll mark 9, 16, 1, 10, and 25 as being available if it's indexed. If it's the linked list, then in order to delete this file, I'll have to go through the file and write down and keep track of the blocks that it used and mark 1 as free, then mark 16 as free. Sorry, then mark 9 is free, then 16 is free, then mark 1 is free, then mark 10 is free. I have to mark them all as free, and then mark 26 as being, or what is it, 25 as being free. I have to mark them. In order to delete, I got to do this goose chase, this wild goose chase, in order to delete a file, because I have to register on this vector that it's free. I could also have a linked list for free space instead of a vector, which could actually be a lot better because I don't waste any space and I don't have to start scanning for who's free. If I did it just like this, I'd have to scan. Could be occupied, 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 until eventually I find somebody that's free, because it's just a linear list. But in a linked list, it's actually a great use of a linked list, because I don't care where these are located. I just care that I'm never going to try to get the 10th one. As soon as I get the one free one, I'm good to go. I'll just give the next file that comes along. I'll give him 2, and if he needs another byte, I'll give him 3. Another block, I'll give him 3. I never need to make multiple jumps. I just make one jump each time I need to allocate a block. So it actually is a great use for a linked list because it's very efficient. I'm never going to want to jump to the middle. I'm only going to want sequential access. And then when I delete some file, I will simply add them to the beginning of the linked list. I'll add them to, in other words, this pointer is pointing to 2. I'll keep track of 2, and I'll make this pointer point to, let's say, 16, which was freed up. So now 16 will be pointed to by the first space list head, free space list head. And then 16, since I kept track of that 2, will point to 2. So as I free up a disk, I just keep pushing them in. So it's actually no need to traverse the entire list.
But if you keep adding a freed space to the head of the list, then it's not going to be sequential anymore, because let's say 14 got freed up, so then you push it ahead, so then the first space is 14, and then you're jumping to 2, 3, 4.
Yeah. It doesn't have to be, who says sequential? It says sequential?
No, like that's the picture. It's all.
The picture, you're right, the picture is sequential just to make it easier to see, but it's no reason that it should be sequential.
Okay.
Absolutely no reason that it should be sequential. Because I don't mind jumping. I mean, you're right, it's a little bit faster if it's sequential, but I'm not, it's always like that in linked lists. You could always arrange them as you insert them, and then you'll save time when you extract them. But let's just keep it simple and just say, if as soon as I want 16, as soon as he becomes available, then I'll make the free space list head point to 16 and make 16 point to 2. And it doesn't have to be sequential. But I'll still have limited jumping around, because I never want to go. I'll never say, give me the 20th space. Why would I say that? All the spaces are equal to me. Now, the thing is, it says you might want to keep track of the number of blocks that are free, because let's say a file comes along and says, I want, 100 spaces, 100 blocks. So we start allocating them and then find out at the end that we can't give it to them. So and we have to unallocate. So otherwise we'd have to go and check, do we have 100? And then I need to traverse. So that's why it says no need to traverse the entire list if the number of free blocks is recorded somewhere. I'll have to keep track. Every time I allocate, I'm going to reduce the number of free blocks. So I'll just keep a running total of how many free blocks I have, so that I know whether or not I can grant a request. And then I won't have to traverse the list just to find out the size of the list. Okay, that's the end of chapter 12. There you go. We did finish 9 and 10 and 11 and 12. So you probably want to review this video because we did a bunch of different things here. You also probably want to review the slides as far as the working set. It's a bit complicated. Does anyone want to ask me a question at this time?
You have
Here, I'll
any
stop the
idea
recording.